Some trigonometric limits. The continuity of sine and cosine. For all real numbers a, the limit as x approaches a of sine x is equal to sine of a, and the limit as x approaches a of cosine x is simply cosine of a. In other words, limit equals value at any real number for each of the functions sine and cosine. Let's find the limit as x approaches 0 of sine x plus 2 cosine x plus cosine squared x divided by sine x plus cosine 2x. First thing we should do here is look at the denominator and think about what its limit is as x approaches 0. As x approaches 0, sine x plus cosine 2x will simply approach sine of 0 plus cosine of 0, which is 0 plus 1 equals 1. So the denominator does not approach 0 here. Therefore, our limit can be calculated as the limit of the numerator divided by the limit of the denominator, which is straightforward to do. Here, the limit of the numerator is sine of 0 plus 2 cosine of 0 plus cosine squared of 0, and the denominator is sine of 0 plus cosine of 0, and evaluating all of those numbers leaves us with 3 divided by 1, or a limit of 3. The other trig functions. Consider the tangent function. If a is not an odd multiple of pi over 2, then the cosine of a is not 0, and so the limit as x approaches a of tangent x is the limit as x approaches a of sine x over cosine x will be equal to sine a divided by cosine a, which is just tangent of a. Notice the odd multiples of pi over 2 correspond to angles which place us either at the top or the bottom of the unit circle, as seen in the figure here. Now, suppose that a is an odd multiple of pi over 2. Then sine of a is not 0, and cosine of a is 0, and so the limit as x approaches a of tangent of x does not exist. So let's have a look at one-sided limits. First, let's think about the limit from the left as x approaches some odd multiple of pi over 2. If x is approximately equal to a, and x is less than a, then x corresponds to either a first or third quadrant angle as shown in the figure here. Therefore, sine of x and cosine of x have the same sign. In other words, they're either both positive or both negative, and so the tangent of x is positive. And from that, we can conclude that the limit as x approaches a from the left of tangent of x will equal plus infinity. Now let's consider the limit from the right. If x is approximately a and x is greater than a, then x corresponds to either a second quadrant angle or a fourth quadrant angle as shown in the figure. Therefore, sine and cosine have opposite signs, and so the tangent is negative, and therefore we conclude that the limit as x approaches a from the right of tangent of x is equal to negative infinity. Now, all of this implies that the asymptote structure of the graph of tangent x looks as it does here in the picture. At each odd multiple of pi over 2, the limit from the left is plus infinity, and the limit from the right is negative infinity. The cotangent function. If a is not a multiple of pi, then sine a is not 0, and so the limit as x approaches a of cotangent x is equal to cosine of a divided by sine a, which equals cotangent a. If a is a multiple of pi, then the limit as x approaches a of cotangent x does not exist, because the numerator approaches either plus or minus 1, while the denominator approaches 0. Now, let's note that cotangent x is equal to tangent of pi over 2 minus x, because cotangent and tangent are cofunctions. Since tangent is an odd function, we can write that as minus tangent of x minus pi over 2. What this tells us is that the graph of cotangent may be obtained from the graph of tangent by shifting by pi over 2 horizontally and then reflecting about the x-axis. So, if a is a multiple of pi, then the limit as x approaches a from the left of cotangent x is the same as minus the limit as x approaches a from the left of the tangent of x minus pi over 2, and that's the same as minus the limit as x approaches a minus pi over 2 from the left of tangent x. And we have just learned that that limit is plus infinity, therefore the limit as x approaches a from the left of cotangent x is minus infinity. And similarly, the limit as x approaches a from the right of cotangent x is equal to minus the limit as x approaches a from the right of tangent of x minus pi over 2, which equals minus the limit as x approaches a minus pi over 2 from the right of tangent x. That limit is minus infinity, so the limit as x approaches a from the right of cotangent x is plus infinity. Here's the graph of the cotangent function. Notice that at every multiple of pi, the limit from the left is minus infinity, the limit from the right is plus infinity. Secant. If a is not an odd multiple of pi over 2, then cosine of a is not 0, and so the limit as x approaches a of secant x is the limit as x approaches a of 1 over cosine x, which is just 1 over cosine a, and that's secant a. If a is an odd multiple of pi over 2, then cosine of a is 0, and therefore the limit as x approaches a of secant x does not exist. Notice that if a is an odd multiple of pi over 2, then a corresponds to one of the points at the top or the bottom of the unit circle shown in the figure. So suppose that a corresponds to a point at the top of the unit circle. In other words, a has the form 4k plus 1 times pi over 2, where k is an integer. Notice this gives us pi over 2, 5 pi over 2, 9 pi over 2, and so forth. Then cosine x, and therefore secant x, changes from positive to negative as x increases through a. Therefore, the limit as x approaches a from the left of secant x will be plus infinity, while the limit as x approaches a from the right of secant x will be minus infinity. So now suppose that a has the form 4k minus 1 times pi over 2, where k is an integer. This is simply a formula which guarantees that a corresponds to the point at the bottom of the unit circle. Then cosine x, and therefore secant x, changes from negative to positive as x increases through a. Therefore, the limit as x approaches a from the left of secant x is minus infinity, and the limit as x approaches a from the right of secant x is plus infinity. This is the graph of secant x. Notice the behavior at the vertical asymptotes, corresponding exactly to the limits that we found here. Cosecant function. If a is not a multiple of pi, then the limit as x approaches a of cosecant of x is 1 over sine of a, which equals cosecant of a. If a is a multiple of pi, then the limit as x approaches a of cosecant x does not exist, since the numerator approaches 1 and the denominator approaches 0. So let's now note that cosecant of x is equal to secant of pi over 2 minus x by the cofunction property, and since secant is an even function, that's the same as the secant of x minus pi over 2. So the graph of cosecant is just a simple horizontal shift by pi over 2 of the graph of secant. So if a is an odd multiple of pi, which corresponds to the point minus 1, 0 on the unit circle, then a minus pi over 2 corresponds to the point 0, 1 at the top of the unit circle. In other words, a minus pi over 2 is of the form 4k plus 1 times pi over 2. And so, the limit as x approaches a from the left of cosecant x is the same as the limit as x approaches a from the left of secant of x minus pi over 2, which is the same as the limit as x approaches a minus pi over 2 from the left of secant x, which we have just learned is plus infinity. And the limit as x approaches a from the right of cosecant x equals the limit as x approaches a from the right of secant of x minus pi over 2, which equals the limit as x approaches a minus pi over 2 from the right of secant x, which equals minus infinity. Now, if a is an even multiple of pi over 2, then a minus pi over 2 corresponds to the point 0 minus 1 at the bottom of the unit circle. In other words, a minus pi over 2 is of the form 4k minus 1 times pi over 2. And so, the limit as x approaches a from the left of cosecant x is the same as the limit as x approaches a minus pi over 2 from the left of secant x, which is minus infinity. And the limit as x approaches a from the right of cosecant x equals the limit as x approaches a minus pi over 2 from the right of secant x, which we've learned is plus infinity. This is the graph of the cosecant function. Notice that at even multiples of pi, the limit from the left is negative infinity, while the limit from the right is plus infinity. At odd multiples of pi, just the opposite happens. Here's a limit that will turn out to be crucial to us later. The limit as x approaches 0 of sine x divided by x is equal to 1. Notice that this is an interesting limit because the numerator and denominator do indeed approach 0 together. One way to think of what this says is that when x is very small, sine x is approximately equal to x, and the smaller x is, the better that approximation is. Here's the graph of sine x over x. That function is undefined at 0, of course, but since the limit is 1, the graph simply has a hole corresponding to the point 0, 1. This is a limit that you're going to want to remember. Now, a proof of this fact typically involves a geometric argument to show that when x is between minus pi and pi, cosine x is less than sine x over x, and of course sine x over x is always less than 1. Then we apply what's known as a squeeze theorem or a pinching theorem that says that the limit of sine x over x, since it's trapped between cosine x and 1, must approach 1 because cosine x approaches 1, and of course 1 approaches 1. In other words, the two ends of the inequality are both approaching 1, therefore the expression trapped in the middle must be approaching 1 as well. The graphs you see here show sine x over x in red, cosine x in blue, and the constant function 1 in black. Also, if theta is a function of x for which the limit as x approaches a of theta of x equals 0, then the limit as x approaches a of sine of theta of x divided by theta of x equals 1. For instance, the limit as x approaches 0 of sine of pi times x divided by pi times x is going to equal 1. And the limit as x approaches minus 1/3 of the sine of 3x plus 1 divided by 3x plus 1 is equal to 1. So what's happening here is that the limit will be 1 so long as the argument in the sine function in the numerator corresponds exactly to the denominator and approaches 0 as x approaches a. Another remark. Let's look at the limit as x approaches 0 of the reciprocal, x over sine x. This limit will be the same as the limit as x approaches 0 of 1 over sine x over x, which will be the same as 1 over the limit of sine x over x. And since that limit is 1, this is 1 over 1, which is going to equal 1. So not only does the limit as x approaches 0 of sine x over x equal 1, the limit as x approaches 0 of x over sine x is also 1. Example. Find the limit as x approaches 0 of 1 minus cosine x divided by x. Notice first that the numerator and denominator of this fraction both approach 0 as x goes to 0. First thing we'll do here is multiply the numerator and denominator by 1 plus cosine x. Now we'll multiply the numerators together to obtain 1 minus cosine squared x, which is the same as sine squared x. Now we'll separate the sine x factors and write our expression as sine x over x times sine x over 1 plus cosine x. At this point, we have the limit of a product where we know the limit of each factor. Sine x over x approaches 1, sine x over 1 plus cosine x approaches 0 over 2, and therefore this limit is 0. This is another limit that's worth remembering. This is the graph of 1 minus cosine x over x. Clearly that function is undefined at 0. We've just found out that its limit is 0, and so its graph has a hole at the origin. Another example. Find the limit as x approaches 0 of sine squared pi x divided by 2 times x squared. Now the first thing we'll do here is break apart the expression into the product of three fractions. Two of those fractions involve sine of pi x in the numerator. Since we have x's in each of those denominators, we would like to have a factor of pi in each of those denominators as well. So we insert a pi into each of those denominators and multiply simultaneously by pi squared. So now we have the limit of a product, which we can compute as the product of the limits. As x approaches 0, sine of pi x over pi x will approach 1, and so this limit is pi squared over 2. Another example. Find the limit as x goes to 0 of 2 minus 3 cosine x plus cosine squared x, all divided by sine x. Again, this is a 0 divided by 0 type limit. We can factor the numerator here, fortunately, and get 2 minus cosine x times 1 minus cosine x divided by sine x. Next, we'll rewrite that fraction as 2 minus cosine x times 1 minus cosine x over x times x over sine x. Notice that we brought in an x into our denominator to match up with the 1 minus cosine x in the numerator, as well as an x in the numerator to go along with the sine x in the denominator. So again, now we have a product, and we know the limit of each of those factors, and so our limit here ends up being 2 minus 1 times 0 divided by 1, which is 0. A final example. Let's find the limit as x approaches 0 of 1 minus cosine 3x divided by x squared. The first thing we'll do is multiply the numerator and denominator of our fraction by 1 plus cosine 3x. That makes the numerator 1 minus cosine squared 3x, which is sine squared 3x. Now, because of the sine squared 3x in the numerator, we'll rewrite our expression as the sine of 3x divided by 3x times the sine of 3x divided by 3x times 3 times 3 over 1 plus cosine of 3x. Notice we've simply inserted a factor of 3 into the denominator of each of the first two factors in order to match the 3x that's inside of sine in the numerator. And we have compensated for that by inserting a 3 times 3 into the numerator as well. So now we have the limit of a product, and we are able to evaluate the limit of each factor individually. Each of the first two factors has limit 1, and the third factor approaches 9 divided by 2. Therefore, our limit is 9/2.